Alright guys, so uh, this is explanation of my project called Algolens. Algolens is a front-end project that I developed to visualize data structure and algorithms, and also a bunch of other things like physics, mathematics, and game zone I also developed. But basically, it is a platform in which it is developed with Create React app, and I thought that there is a need of a tool to for the community to understand data structure and algorithms better. So it started primarily with that goal in mind, but then in the future, I'm also planning to add various other concepts like computer networks, operating systems, and cryptography and AI and machine learning. But right now it's only algorithms and data structures. So there are a bunch of cool visualizations that I want to show you. But then let's go through the basic of this platform first. So this is a header section and then a basic main content and then a footer section. Okay, so let's go to the code of that. But that is the interesting part. So this is a Create React app, and just like any other Create React app, we start with the first index HTML file, like the index file in which we basically render our application. So in the app folder, I have basically put up a theme and then a error boundary on top. We'll get into the error boundary first. So the error boundary is basically a class that has some any kind of error is gonna catch, and then also allow the reloading of the page. So something went wrong, and then show the error message to the user, and then handle the reload. Okay. So this is a basic component, wrapper component across the entire application, and then some primary styling for the theme, right? Then a site header, and then a router section, and then a footer. So the router basically is my main page content. Doesn't seem like it, but basically I use a router switch, which is the React browser routed from router DOM. So I've used the hash router and route and switch, and I'm lazy loading the dashboard in the main page components, and then I basically put up a structure uh, in my application for the loading of the routes, and same structure basically also helps with the auto suggester of my site. Okay, so the site suggestions are basically I basically put up a pages structure. Inside pages I have a category, and for each category page I have a subject. So I generate a path based on the category topic and subject topic, and then a route. Okay, and then basically a title. So title helps me to render it on the auto suggester, and then all the suggestions basically I export out of my structure. So my structure is simple. For for the topic of algorithms, in my site I have algo folder, then uh, inside that we have pages. So topic label is algorithm, and then category label is a star pathfinding. Okay, so the a star pathfinding is my algorithm inside my algo folder. Then for example, inside that index.jsx, this will be rendered by the my route by my hash router switch, and this will show the algorithm. Okay, so let's just go into the algorithms one by one, and then data structures would be easy going forward. But ideally, we should do data structures first. But there's a few problems with the data structures I've developed so far. So we'll skip the array because it's not working currently properly. But then let's go with binary tree. So this is my binary tree visualizer. Okay, this is an interesting thing. So I insert say 12, it creates a node for me, and then if I do 5, it inserts 5 to the left of it because 5 is lesser than 12, and then if I do 7, then it basically finds the proper position for 7. So it basically maintains an order like a binary search tree, if you know about that. So basically binary search tree is order maintaining set in which a tree set, basically, in which you basically put the values inside either left or right, but it always maintains a property. Property is that the left children's are always lesser than the root value, and the right children's are always greater than the root value. Can be greater or equal as well. So, like if I insert 12 again, what do you think? Will it go left or right? So it will go to the right. So the right ones can have equal or greater values. And then say if I put 10, right? Then 10 will be after 7. So if I want to search say 5, uh, then it will highlight 5. Okay, so this is the functionality of my visualizer. Okay, so this is a basic. Let's go into the code of this. So this is a very interesting part. So inside ds components binary tree. Okay, so my index.jsx file has the binary tree, and then in this so basically I have created a data type called binary tree. Let's understand how that works. So my binary tree has a tree node. Every node will have a value and a left and a right pointer. Okay, so at the constructor level I say that my root node is null. Then I insert a new tree node, and if my root is empty, then I assign that new node to the root. Otherwise I insert a new node inside my tree. So for insertion logic I will check that if the new node value is lesser than the node value, then I want to insert it at the left. Otherwise I want to insert it at the right. Okay, and to find a value for finding operation, I will say that I want to check whether it is gonna be if it's gonna be lesser than the node value, then I'll search in the left space. Otherwise I'll search in the right space. Otherwise it will be equal, so I'll return that node. For deletion also similar logic. uh, what I'll do is basically for the value to be less than the node value, then I'll say okay that I need to basically reassign the left value with the deleted part. Okay, otherwise if the value is greater than the node value, then I need to assign the right value with the deleted part. uh, Perform the deletion operation and update the right tree. Okay, and if both left and right are null, then I don't have any node left. Okay, because this is the current node that I want to delete. And otherwise if the left is null, I return the right node. If the right is null, I return the left node. Otherwise I find the minimum node which should be removed, and then set its value, and then delete the right node. Okay, so the minimum node I can find by going left always. Then there is this clone function. Basically what it does is uh, this clone function, what it does is basically it creates a replica of the tree. So every node, it basically recurses left and right, but before that it creates a new node with the same value, and then it basically assigns the left to and right to the clones of, basically clones the current node and the left tree and the right tree, so that clones the entire tree. Okay, so this is my binary tree data type. Now I create a binary tree in my react node, in my react state. Okay, and then for the input I have a input state, for the search I have a search state, and the found node is the node. Then I basically create a canvas, and in the canvas I create a context, and then basically for the canvas I set its width and height, right? And then clear the context. Then I basically call the render tree method on my uh, tree root, and uh, I'll just go into what this render node is. But uh, okay, so render tree, right? So I say that my radius of my node is 20 pixels, and the gap between two uh, two subtrees would be 50 pixels, and then a line width would be of 2 pixels. Okay, so basically I start my canvas, I create an arc at xy position. Okay, and then uh, basically the radius, and then it is a 360-degree, matlab two, it means to say that 2 pi, 0 to 2 pi arc. Okay, so complete circle. Then I put a fill color. So if the found node is equal to the node value, then the color is highlighted, otherwise it's the normal green color. Then I fill it, and then I put a stroke and line width, and then I fill a text of the node value at the xy position. Okay, and then that is in the center. Okay, and if the node left is there, then I calculate a new left gap, and then for the y height I put a increment of the gap, right? And then basically I uh, move the context, then I draw a line from x left to y left minus radius. Okay, uh, and also render the left subtree, and if there is right subtree, then similarly I put a x, I have calculated the x right and the y right. Okay, and then I basically move my context to x to y radius, and then draw a line from x to x right and y right minus radius, and then I render the tree of the right side. Okay, so for the input I basically use my input tag to basically set the input value. Then I handle insert and handle delete. uh, then for the input I also put a search value state, and then I render my canvas with the width of 800 and 600 height. So basically this is the code of my binary tree visualizer. So render tree function is clear. Now there is handle insert and handle delete. So already I have a tree data structure with me, right? So basically I take the old tree, I insert the input value inside it and clone the new tree, and then return the clone version of that tree, right? So every time I am inserting into the tree, I cannot have the reference because in the set state function we cannot have the same reference. We have to mutate our reference, right? So that's why I have to clone the tree, and then basically I put the input value as null. Similarly for the delete function also, I take my tree and then clone it, and then basically delete that value and then clone it. And then for find also, uh, I just find the node in the tree and then set the found node as the node, and that basically helps me to find the tree. So these are the functions that are there. It uses a bit of canvas, requires knowledge of working with the canvas a bit, but once you understand the basic functions you can develop such visualizers yourself. So I hope this video gives you the motivation to understand how basically you can develop a UI to visualize algorithms. So this is binary tree visualizer. Next is next in the tree structure is B plus tree. Okay, so B plus tree is a variation of B tree. So before going to B plus tree, we will go into B tree. So let's do B tree first. So B tree is basically a self-balancing tree data structure, okay, in which you can maintain sorted structure, and you can search into it, insert data into it, and delete data from it through logarithmic time. It's basically used in databases and file systems. Okay, so let's say I want to keep at one particular level 6 entries. Okay, so I'll just initialize this. Okay, so it says that the current order is 6, and the maximum keys per node is 5, and the minimum keys per node is 2. Okay, so let's just load an example. Okay, so the example B tree is minimum keys is 2 and the maximum keys is 5, so we have 20 lesser elements in that. Then this is the range of 20 to 40, 25, 30, 35, and then this is greater than 40. This is 45. So these are leaf nodes and these are self-balanced tree. This is a self-balanced tree. Okay, so if I want to insert something like 67 into it, right, then basically it basically says after 45 and 50 you have 67. Let's say we insert something like 13 into it. Okay, so 13 is inserted. Now there is a bit of an operation going on. What happens is that we had 20 and 40 only initially, and 5 and 10 were neighbors in the leaf. But now 10 got promoted and 13 got into the leaf category as a leaf node. So 5, 10, and then 13, 15, and then 20, then 25, 35, 30, 35, and then 40 and 40, 50 and 67, as you can see in the diagram, this diagram. So let's just understand how this basically works, and then before that we also see a demo of the searching part. So let's see if I put 45, right? So 45 is found and then it is highlighted here, right? Okay, it basically has a validation also. This form has validations also, that you should enter a valid number. But let's say if I put 30 here, right? So it basically highlights 30 is found. So I highlighted it as red. Okay, so some properties of B tree are that B trees are balanced. Okay, so all the leaf nodes are at the same level, and then each node has multiple keys and multiple children, and then keys within nodes are in ascending order, and also uh, node capacity is also there, and then basically node with k plus k keys can have k plus 1 children, and root can have fewer than minimum keys. So this is the uh, example walkthrough of the demo. Let's just go into the code of this. So B tree. So for B tree, I have a class called B tree node. So it's very simple. The B tree node has an array of keys and an array of children keys. An array of keys and array of children. Okay, and at every level we mark whether it's a leaf level or not. Okay, so at the constructor level, generally we are initializing with the order 3, but then the root element is a B tree and root element is initially a leaf node. Okay, then later on going forward, basically initialize the order for the B tree, and then minimum keys is basically the order by 2 minus 1, and then maximum keys is order minus 1. Then we perform the search operation. So we're given a node which we have to start the search on, and then we have to basically identify the key. So while the key is greater than the node keys index, so basically we are searching at the current node, and there are some keys in that node, right? So across the keys we are basically searching. So if the key is greater than the node keys, then we keep on incrementing, and if after incrementing we see we're going in a sorted fashion, so if the key matches the node key we return true. Otherwise, if the node is leaf, we say it is a false. Otherwise we basically start searching from the ith children. Okay, so this is how we find the keys. Insertion is simple. So if there's one edge case, for example, if we have reached the max keys, then our root is full, so we need to create a new children, and then in the children we need to push the current root. Okay, then there is this function to split the child, and then the root becomes the new root. Okay, otherwise we just insert from the root the keys. So the logic is that, say you have a bunch of keys, right? So if it is a leaf node, then you basically push the key and you sort the keys at that leaf. Okay, otherwise you have to figure out which key to insert, which child to insert into the node. Okay, so then from the children you see that if the child is full you have to split it. Otherwise you basically say that okay, key is greater than the current key, then you increment. Otherwise you basically insert at the children. Then basically how to split the children, so you basically start from the parent node. So from the parent node you say that okay, it is a full child, and then if it is a leaf, you basically create a new child node out of it. Then at the mid index you basically take the maximum keys length and then divide it by 2, you will get the mid index, and then the mid key is the uh, child at the child at the mid index. So basically take the new child keys at as the mid index. The keys after the mid index are the new child keys, and then you remove the middle key. So if the children is if it is not leaf, then basically you take the new children, new child's children as the full child children from the mid index, and then the parent keys, right? You basically splice. So the index, from the index, you basically add the mid key from 0 to mid key. You splice it out, and also for children, you splice it out at insert the middle key into the parent and also the children. That is it. Now how to get the height of this tree? Okay, so if your node is a leaf, you return 1, then basically it is the one height. Otherwise whatever is the height of the first children, okay, you get height of that, and then you increment 1 into it. By default the root node is the height. By default the node is the root node if you don't provide any node. Then how to clone this tree? So basically you basically take this order and you create an entire constructor class and then assign it to true, and then basically you clone the node, and you basically say that recursively you basically clone all the children. Okay, so basically for the new node keys it's everything as the node keys. This is a split operator. Okay, and then for the children you basically clone every node. Okay, so that is the children. Now this is our B tree class implementation. Now what we'll do is we'll basically see the visualizers React component implementation. So initially we have initialized our order, we maintain it at a state, and then we have tree. That tree is also our B tree state. Then we have an input value, search value, and whatever are the highlighted nodes, and what is the last operation. So for initializing, we basically take an order value, and then if the order is less than 3 or greater than 7, then we do not accept that. But if our order is in that range, then we initialize the B tree of that order, and then we basically set the last operation, and then highlighted we don't have any highlighted nodes initially. Then we insert, so we take an input value and we ask to insert a valid value, and then we clone the tree and insert that value inside that tree data structure, and then set the new tree, and then we set the last operation as we have inserted this value and highlight the nodes as the value node. After some time we remove the highlighted node, I mean we clear the highlighted node. Then we have handling of search. So we take the search value. If the value is not provided, we say that we should have a valid number, right? Then up in the tree we perform the search operation over our tree data structure, and then after that we say that we search the value and we found or we do not found. Okay, if we have found, then we highlight the value node, otherwise, and after some time, 2 seconds, we basically clear the highlighted nodes. Now if we click on load example, then we basically take a bunch of values, and for every value we insert it into a tree. This is some static values that we take, and then we set the tree, and then we say that we have set the last operation as example B tree. Then we render the node. So at the so we take a start node and then an x and a y, right, and then a width and a level. Okay, so node height is 50, key width is 50, node width is whatever is the key's length into key width plus 10 for the gaps, and then uh, the maximum value can be 60 for the node width, and then we have a vertical spacing of 100. So to draw a box, we use the rect class, rect tag, and then we provide an x and a y and width and a height. Okay, and then we push it into our elements. Okay, so for each key, we take the key x and we check whether our highlighted node is highlighted, and then we push into our uh, line, push a line element. Okay, and then we say that from x1 to y1, x1 y1 to x2 y2, we basically have a line. Similarly, we also put a text tag. Okay, so then we have key x and then y, and then we put a key value inside the text tag. Then we draw children. So for the child width, we say that we divide the child width by the node children length, and for every child we calculate its x value, which is calculated like this, and then we push the element. At the element, we push, basically we push the line from parent xy to child xy, and then for y we basically maintain the node height and the vertical spacings. Then we recursively start rendering the childs. Okay, for the leaf we basically push a text called leaf as well, and then we return these elements. So we calculate the tree height, we get the tree height, and then also svg height is our tree height into 120 plus 100. We just do a simple calculation of that. So this is our description tag for the B tree visualization. Then we initialize B tree and then we maintain an order to give an input tag for order. Then we give a button for initialize, and then button for loading the example, and then some basic information about the tree, how many max keys and how many min keys and what is the current order, right? Then we provide an input to insert the key and a button to insert, do the insert operation, and then a search button and an input, and then we also highlight the last operation, and then we render the node for the tree visualization. Then we basically highlight the properties of the B tree, and then we also have some section for the time complexity, and then also the data set, and also the uses of B tree. What are the real world applications? So if you see, if you go down, this is the property, and then this is search, insert, delete, and space is on, and then all of these operations are login, and then we basically give the real world application, which is like most of the relational databases use B trees for indexing. What is indexing? Indexing is basically putting a record for your database to basically put a mapping of which entry should be at which disk block, or like wherever in the database you're storing it. So basically B trees maintain that indexing record. Then we have file systems. In that also we basically use B trees for file organization. So Windows uses, for example, NTFS. Then for data that doesn't fit in memory, we can also use B trees, and also for range queries we also use B trees. So why do we use B trees? B trees basically are good for working efficiently with the disk storage or the block storage of the disk, and every node fits in the disk blocks, right, and it minimizes the disk IO operations, which is much higher in real systems. So this is about B tree. Okay, next let's just do a simple structure which is linked list. Okay, so uh, basically let's just understand via diagrams. If you don't know what a linked list is, we'll understand it via diagrams. Okay. So this is uh, okay. So this is a linked list. Okay, so a linked list has one second. Okay, so let's just let's just try to understand. This is my head node. Okay, and this is my tail node. Okay, and this is my data, let's say 12, or anything. Like this could be not necessarily it has to be a number, it can be anything. Okay, but let's just work with numbers right now. Okay, and then we'll understand. So a linked list is basically a collection of data, linear collection of data, and how it works is that you start with a start node and then you have an end node, but then there's a reference from one node to another, which is a pointer reference to the next node, and then that is how basically you form a linking between two nodes, and this is how you form a structure of which you can traverse and store data in. Okay, so this is a data structure. So the use of linked list is to when you have sequential data, right? But when you can't work with arrays, for example, like you want to maintain data, but you want to access only the uh, start or the end of the data, and then you don't want, for example, you don't want to search through data. If you have to scan the data, then you have to go one by one. So you have to start from the first entry and then you have to go into the next entry, and that is how you find something, look for a match. Okay, so it is not necessarily a very efficient structure because there are better structures than this, but it is a good structure to sparsely allocate data into your memory. Like you don't need to have a contiguous block reserved for your memory, like in the example of arrays. So it doesn't have enough access time, but it has a very good practical applications. So this is a linked list. So to understand linked list, let's just do some operations and then understand the code behind it. So I check on the insert, and then it opens a menu for me in which I can choose a position. So if I want to insert to the start, I can say want to insert 23. So basically it inserted 23 at the 0th position, and this is the head as well as the tail node. Okay, now if I want to say insert something like 56 at the end, okay, so I choose that. So it says after 23 the next node is 56 at the first position, 23 is at the 0th position, and then that is the tail. If I say start and then if I say 13, then 13 is at my 0th position, and then 23 comes, and then 56 comes. So you can insert at start or end, right? And if you want to delete, then also you select a position, right? Generally start or end, but you can also specify other kind of position like index. So if I specify the, let's just insert more data first. So I'm gonna insert 33 this time at start. So just to have more data. Okay. Now if I want to delete something, I say delete at index 2. Okay, and the value, okay, so this is the index 2, so it removed the index 2. Now I don't have 20 in my dataset anymore. I have 33, 13, and 56, and it's pointing to the head here and the tail here. This is my linked list data structure. These are the operations I provide on it. If I want to update something, I can say that at index 1 update the value to say 34. Okay, so at index 1 it highlighted as well. So this is how you visualize a linked list. This is a visual representation of a linked list. And if you want to search something, that also you can do in this. So the say I want to search 56, so it has highlighted 56 for me and says that it is at the tail position. Let's look at the code now. So inside my DS I go to linked list, and then I see the index.js. So basically for every linked list we have two things which have head, node, and the entire list. Okay, so then we say whether we have rendered or not, and then we have radio for operation. So selecting the current operation is basically at the radio bar. Okay, so there is this one function, clear will commit to it later. This is the insert function, will commit to it later. Let's just see the JSX part of our code first. So our JSX part is we basically have the bunch of operations. We have the input. Okay, so first is my insert. Okay, next is my delete. Then other one is my update. And then this is my search. Okay, so on click of these, on change of my input, I'll basically change. So basically this is the label for that ID. So what I'll do is this is my input type radio, and then uh, show operation. So this show operation function, it will take the target value and set the root radio value as the target value. So the target value would be delete in this case. For example, if the user selects the delete option. For example, for insert it will be insert. Okay, and for update and search it will be update and search. So this is the value that the operation variable will hold. Okay, so now when the radio val is equal to insert, we'll open the insert dialog, and then this is a component for that. Okay, so we'll get into that. Then for search we'll have this, and then in the insert we will call the insert function, and in the search we'll call the search function, in delete we'll call the del function, and in update we'll call the update function. So all of these will call their functions, and then we'll render the list. So the list, so basically for the insert function we'll have data in there. So we'll clear first everything, and then we'll create a new node with info, next, and highlight. Okay, then if there is no head, then new node will be our head. Otherwise, if we selected the operation to be start, we'll say that the new node next is head, and the head will become the new node. Otherwise, if it's the end, or if it's the default case, if nothing has been selected, then we'll say that we will iterate over the list, and then when we reach the last pointer, then we will say that okay, we'll assign the new node to the current next, to the last one next, and then we'll set the head, and then we'll say rendered is false. Okay, for insert this is the logic. For delete, again, if we have head we'll clear it, and if we have head 1 we'll set it to head. So while the head info will be equal to data, we'll just uh, basically assign it to the next pointer. Okay, so we'll start from head, right? And then we'll assign the next pointer to the we'll skip the pointer. Okay, similarly, if the position is matching, then we'll also skip the next pointer. We'll delete the element. So for deletion, what we have to do is say this is the node we have to delete at some position k. Okay, so at k minus 1 we'll reach first. Okay, if it's not head, okay, then we'll reach at k minus 1. Otherwise, if it's head, we'll just point the head to the next one. That is it. That is quite easy. Okay, but if it is uh, some middle position, or if it is the last position, then there are cases. So for the last position, it's easy. We just take the tail point one before the tail pointer, and we'll just remove the tail. Okay, so basically we just say that one before the tail, next of that would be null. Okay, and then we'll just free the point, free the tail. Okay, but if we have, but here we have sorry, what do we have? Yeah, we have. Okay, so if we have some middle node, right, then we have taken the case of head and we've taken the case of tail. But if we have a middle node, then we will reach the k minus 1th node. And what we'll do is we'll say that the k minus 1th nodes next is skipping the one that we just have at the next. So it will take the next to the next because we already know that the next node exists, but we'll just take the next minus one. Okay, so that is the logic which this does. Then for update is also simple. We'll start moving from current to the next, and then once we say that okay, we have decremented enough position, right? So we'll say that we will highlight this one, and we will set the current info to the value, and then uh, update the value at that current. Okay, otherwise our position will be out of bounds. Similarly for search, we'll say that if the current info is equal to data, then we'll highlight and we'll keep moving. Okay, and then we'll just set the head as new head. Okay, and rendered as false. Then for render list, we'll say that okay, we're gonna push a fragment, and then we push an element of type linked list. We already seen that what an element is, and then we'll highlight the current element. So these are the operations, and then we are rendering our list at the end. And in a use effect, we'll manage the rendering of the list every time our data changes. Our basically uh, every time our state updates, we'll just render the list if it is not rendered right now. Okay, so after that, let's go to the next data structure, which is stacks. So So let's understand stacks now. So stacks is a data structure which is quite useful. Uh, so basically, um stack is basically a data structure in which you basically maintain insertion order, right? So you start from the bottom and you keep inserting on top of it, and it's generally used in programs to maintain function calls or your context variables. Okay, so function calls and context variables are stored in the stack, and then basically compilers also use stacks, and to maintain the, and even your browsers uses stacks to maintain the various URLs that user has navigated to, right? So basically stack, to get the intuition behind stacks, stack is a data structure in which you have a bottom and a top, and the top is, I mean, the stack is dynamic. This top can go to any place, any value. Like you can store any number of elements in the stack. The only catch is that you basically have a reserved amount of memory in your RAM, right? So once your stack reaches some threshold, after that it will be a condition of stack overflow, so you just generally have to take care of that. So your stack grows one by one in the one by one in a upward direction, right? If you can visualize it like that, like a stack of plates, and then whenever you have to take out something, you take out the top element, so the top plate. Okay, so this is very simple. So let's just understand stacks as, again, just like any data structure, you can store any data inside it, but we're gonna go with integers. So let's say we have 34, 56, and 78, and 9, and 11, for example. So from the top, if we want to say that, okay, I don't want 11 anymore in my data structure, so we'll just remove it. Okay, so now my top becomes 9 and this 11 is gone, right? And if I want to insert a new value, then I'll say I'll insert 101 and my new top is 101. Say my stack was of only 5 elements. At this point my stack has overflown. Okay, like if I want to insert any other element, I will have to throw an error that, okay, I can't insert anything more than this. So stacks can be implemented via linked lists also and arrays also. Both are viable options to implement stacks, right? uh, Generally, okay, so let's get into the platform demo first. So we have push. Okay, so again, when I choose an operation called push and I say that I want to insert 45, so this is my stack container, top element is 45. Now I want to insert 78, so my stack container top element is 78, 45 is below it. Then 89, so 89 is the top element. Then 12, 12 is the top element. So I, you see how the stack is growing. Now if I pop out, right, I'll just say 12 is gone, so my top element is 89 now. Again pop, again pop, again pop. Now I can't pop anymore. If I say I want to get, then it says it is an empty stack. If I push something, if I say push 34, and then I push 67, and then I push 89, and then I push 101, right? If I say I want to get, if I say I want to get a top element, then it will reply with 101. Otherwise, if I would want to get the bottom element, it will reply with 34. Okay, so there are a bunch of things you can do with a stack. Uh, it can appear in data structure and algorithm problems. There are very many ways to work with stacks, and stacks are generally used in programs for maintaining function calls, as I said earlier, and variables, context variables. So let's just understand the implementation. Okay, so again, in our data structure folder, we'll get into stacks. So I render everything as an element, and I have push, pop, and get operation React components for those. Okay, so I'm implementing stacks as arrays. So I basically kept an array and an array of and a set of highlights, and also then this where this can be top or bottom, and then the result that I want to store after an operation. So, and then the radio value. My container style is there, and my paper style is there, and my card style is there, and my header style is there. These are my some of my styles. Let's just skip that. Okay, then this is an operation. So on click of a radio value, I just set my radio value as the target value of that input value, and then basically that is my operation. So for the push, it takes a data argument, and then at the 0th index it basically inserts the data and then updates the array. Okay, and then set highlights to the 0th element. Okay, for the pop, it basically takes one element out of the array at the 0th index and then set the array to the new array, and then highlights also. For the get, we basically have the where condition, which is top or bottom, and then we set the highlights and the result. For the bottom also we set the highlights and the result. Okay, so this is my render function. It's an input label with the push. Okay, for push value, for radio it is a radio button. Again for pop it is a radio button, and for get operation we have a radio button. Okay, now for the push radio button we call the push function. For the pop we call the pop function. For the get we set the where value, and then we render the result in the array and we call the get function. Then for the array we basically render the element by element. Then this is a stack container placeholder div. So we render the element and we say that okay, for every element we just want to highlight it or not, and then data has a value and an index, and we basically render it at a stack. So this is my implementation of my stack using a React to visualize stacks better. Okay, so for today we'll do one more. We'll do a few more. Okay, so let's do queues. Again for queues, let's understand queues. Okay, so let's just cut it out everything. Okay, so queue is simple. Queues are generally used to maintain, uh, say you have to do some, again queues can be implemented by both arrays and linked lists. Queue is a data structure in which you basically have a front and a back, right? And in the context of computer programming you basically maintain queues to, uh, say you have a scheduler. Okay, task scheduler. So basically it can maintain a queue of tasks, and then it can process every task one by one, and then once the queue is empty it says okay, my queue is empty, so all of my tasks have been produced, have been done, and then it can free the, uh, it can free the IO, free it for the further IO. So my main CPU is idle now. Okay, so the CPU processes the queue of tasks. For example, you say that I want to print a sheet of paper, then or a PDF. So you can basically put that job into a task queue. And then if you want to run a software and if you want to play a game, then that game is basically running in a loop inside a queue. Okay, so this is how queues work. So you can visualize queue as something like this. It is a structure, right, which has a front. There are variations of queues also, we'll get into them later. I've not developed visualizations of those right now, but let's just understand the basics. So this is the front. Okay, and then if I copy this and paste this, or let me just not do that, and then this is the rear. Okay, let's just assume that this is a queue of integers. So this is 34, 25, 23, 32, and 41. Okay, so this is a bit of, this is a basically sample queue. Okay, so say I want to, so basically the insertion happens at the end. Okay, so always this will grow in the right direction, and the deletion happens at the start, so this will shrink it the left direction. Okay, so uh, so basically if I say that the 34 is done, so basically this is gone, this is eliminated, and then front becomes 25. And if I want to say that okay, 25, 23, I want a new member into my queue, somebody new, some new job has entered in my queue, then I would say that okay, this is the say 63 here. So this is the rear element now. This is how my queue can grow and shrink. It is a dynamic data structure that can be implemented with linked lists or arrays both. Okay, so let's just see some implementation in React for this sort of component. So again, in my platform, what I've done is I've provided the operations. So it is a first in first out structure, right? So 67 I submitted, so my head and tail is there. Now if I implement 89, so it is entering at the end. Okay, it will always insert at the end. Okay, so my tail is 12 now. If I insert 23, it will be inserted at the end. Okay, so this is my tail. Now if I delete something, delete will be from the front, so 67 is gone. If I update something, I'll say that I want to update the value at index 2, right? Then the value becomes 13, so from 12 it will become 13, and it also highlights it. So we'll see how I achieved that. And then for the search, say my value is 78, so I submit it, it's not found. If I do 90, submit it, it is found. Okay, so this is my data structure visualization for this queue. Okay, now let's just see how I implemented this. So for the queue, I maintained a list and a head element, and then I have a flag for whether it's rendered or not, and also what is the current operation value. So this is my radio value. So let's just go into the JSX part. Okay, so I basically have an operation and a bunch of radio inputs. So for the first input, I basically say insert, and then for the second input I say delete, and then for the third input I say update, and for the fourth input I say search. Okay, all right. Then okay, so this is my radio values. All right. This is my radio values. So what does this do? These operations, whenever this radio value changes, this basically sets the operation radio value to the either insert or delete or update or search when you click on them. And basically based on that, I basically render these insert, search, delete and update components, which are basically open or closed, and then inside those I call these functions of insert, search, delete and update. Okay, and then I render my list. So let's just understand the list data structure. So this data structure list, how I set it up is, because it is a JSX, how I set it is I maintain my head structure and start from the head, and then I push into my list every element for for every data structure, and then I render it on the screen. And also I maintain what is the info, what is the key, and what is the next value, and then highlight. Okay, so basically this is rendered as a type of linked list. My queues are implemented as a linked list. So for the insert operation, what I do is I create a new info node with the data value, and then I said if my head is not set, then I basically set my head as this node. Otherwise, I basically insert this node at the end. Okay. Otherwise, for delete, I basically take the head to the next value of the head, and then update that head as the new head, and then that basically does the deletion logic. For update, I basically traverse the linked list uh, to one position before what I have to eliminate, and then if I find such a thing, then I basically change the value and highlight it, and then set the new head as the clone of that current value with the as the clone of that. Okay. Now for search what I do is, basically I check whether the data I want to search is the current nodes info. If yes, then I highlighted it. Otherwise I don't. I just keep traversing forward, and then once I've done my traversal, I just set the head as the current, as the clone of the list. Okay. So this is my queue data structure. I hope you understand this very well through this visualization platform that I have built. I hope it makes it clear. So for today, I have covered arrays, linked list, stacks, queues, and B trees. So I hope that is enough for today. In the next video, I'll cover a bunch of other data structures, and I'll show how I have visualized all these data structures. Thank you. See you. Bye bye.